Okay, so I'm happy to introduce Jon. He'll talk today about modules with finitely generated cohomology.
Okay, thank you. So before I forget it, let me say that this is going to work with Dave Benson. Who once was a professor at the University of Georgia. If you've seen my talks, you probably know what the ground rules are, but basically it's G will be a finite group. And K will be the field of characteristic P equals 0. Okay. So I'm going to write down a conjecture. This was that sort of started all this off in some sense, or revised it depending upon your point of view. And this was I discovered this when I arrived a year ago in Bonn at the Hausdorff Institute, and Dave Benson and John Greenlees were there. And Greenlees had made this conjecture. John Greenlees is a homotopy theorist at the University of Warwick, in case you all don't know. But his conjecture goes like this. And I will attempt to explain the notation in a minute. It's the modules or complexes over C star of BG. It's generated by the S. S is the total. Okay, so what does this mean? All right, so C star of BG, our BG is the classifying space. Of G, and C star of BG is the cochain. On BG. So this is sort of like, you've got you build this classifying space. I'm not going to go deeply into this because it's not going to be germane to most of what I'm going to say. But you build this classifying space by you put in the points, and then you sew in lines with which are group elements, and you sew in then you sew in a larger thing, which homotopies, which represent the relations among the group elements, et cetera, and you want it to be a k pi 1, so you want to kill all higher homotopy in this. But anyway, you get this space, and you get the cochains on that, which means you take a complex of this, and this gives you a differential graded algebra over K. We're going to do cochains on BG over K. It gives you a differential graded algebra, or you can consider it as an E infinity ring spectrum if you're into that kind of thing. I hope nobody asked me for a definition of that, because I'm not sure I can give you one. But anyway, so what they want today, so that's the cochains on BG. The derived category is the category of complexes. The bounded derived complex category means complexes of finite length. Okay. In the derived category, morphisms, of course, chain maps. And you go one step further, you invert any morphism that's a quasi-isomorphism. Okay, just sort of throw in an inverse. Quasi-isomorphism means it induces an isomorphism of homology.
Do you mean they use DG modules probably for lower instead of DG?
Yeah, you can do that kind of thing. I'm not.
You don't mean that. No, I don't know what you mean.
Oh, I'm sorry, what do you
Are you
think?
taking DG does modules mean like? They have a-
Yeah, they've got to be compatible with all this structure that you have on it, yeah. Okay, so, all right, so he wants to say this. What he means by generated, we'll get into this a little bit more, is that you can get this by taking this particular module and you take shifts of it and you take triangles that you get into it. This is a triangulated category because after all, if you're talking about complexes and you have a morphism between two complexes, the third object that you want is a mapping code from that. But this isn't an exact sequence. It gives you a triangle because you can go one step further and get back to the shift of the original domain. And we'll talk about that a little bit more too. So when you're generating this, you're taking shifts and you're taking triangles and forming third objects in the triangles, et cetera, et cetera. And what I'm saying is you can get everything by that method. Okay, so there you are. So
Now, is there any like homotopy theory to interpret? Isn't C star DG basically like the homotopy theory of DG? I think that's something like that. I'm just asking.
yeah, sort of. It's like sort of like taking a projective resolution. I mean, you're going to take this cochain, this complex of simplicial complex, something like that. And these things are defined really only sort of up. I mean, there's a lot of homotopy that goes on in here. Okay, so in the usual way things are often done in mathematics, when you've got something like this that just looks absolutely impossible to deal with, you try to translate it into something that's a little less impossible, maybe. And so we want an equivalent conjecture. And this equivalence is by both Dave Benson and John Greenleaf. And it goes like this. It goes that let me make sure I get this right. Okay. What we want is in the stable category. Which I'll write as this. KG modules. The subcategory of modules with finitely generated cohomology. Is generated by two things. First, one is a subcategory of finitely generated modules. And the subcategory of what we'll call no cohomology dash set. Okay. So this is a somewhat better statement because you're actually getting into a smaller category in some sense. It's not surprising that cohomology comes in here, because after all, if you take the homology of this cochain complex, you're gonna get the cohomology of the group, is basically what it amounts to. But let me see if I can, so to go through this, there are a few things that we probably need to explain. Finitely generated cohomology, finitely generated modules, no cohomology module. Okay, so what do we need to explain here? All right, well, first of all, what's ST mod? Well, in the objects here are KG modules. And we're not assuming finitely generated. And the morphisms, well, if you want to harm in the stable category, we usually put an underbar on that. KG M to N. Or you just take ordinary homomorphisms. And you factor out those that factor through a projective. So these are the ones that factor through projectors. Module. And what by factor, I mean, you can write it as a composition of two things where the thing in the middle is a projective module. That's basically it. So this is what you've got. This is a triangulated category too. Because basically, if I've got a map from M to N, I can make it into a triangle. And the way you make it into a triangle is you add a projective module here, or some projective module, so that this thing is now injective. All right. So you add something that's just big enough so that you get it to be projective, and then you take the kernel. So I've got 0 here, and then you take the blue kernel. And that's the third object in your triangle. And the amazing thing is, if you take N and you look at the map into the kernel, okay, then what's the third object? Again, you might have to add a projective. What's the thing you get? Well, what you get is something that we usually call omega inverse of M. In other words, you're sort of back here, only you've shifted. And what's this omega inverse? Well, if I take M and I map it into its injective pole, then the co-kernel of that is omega inverse. And so what happens is, if you go around the triangle, go to M to N to whatever this thing is, then what the next thing is omega inverse of M, and you can keep going around the triangle. So it's a triangulated category in that sense. All right. So this is something that we need. All right. Let's see. Yeah, we will probably come back to this, but we do have this triangulated structure on things. What do we mean by finitely generated cohomology? Well, H star of GM is a module over the cohomology ring. Okay. And so what we want is we want it to be finitely generated. So M is a finitely generated cohomology module. If H star GM is finitely generated. Okay, that's easy enough. All right, I will point out, by the way, that by an old theorem of people like Jon F and some others, if M is a finitely generated module, then it's a finitely generated cohomology module also. That is, finitely generated modules always have finitely generated cohomology. Okay, all right, what's next? Okay, well, we have a subcategory. And that's the subcategory of cap ST mod KG. Okay. Say consisting of finitely generated modules. And so that's what I mean by this. And finally, let's say we need one last thing, that's no cohomology module. So what's a no cohomology module? Yeah. If the cohomology is with coefficients in M is exactly 0. Okay. And so there are a few things we want to say about this. Well, I guess the main thing we want to do is maybe we should go through and talk about what these things actually are. I would count, we're doing this in the stable category, by the way. So if M is a projective module, it's 0 in the stable category. So basically what we're looking at is we're looking at tape cohomology, if you would like. But projective modules would satisfy this. But there's another thing that happens in this. And that is that we can in fact that we can actually say something about what these look like. This comes back. But before we do that, let me just say, all right, so what we want is this subcategory of finitely generated cohomology modules to be generated by these other two. And that is, exactly the same idea. You start with objects in these other two categories. If you've got a map between two of them, you take the third object in that category, you throw that in, and then you do it again, and you keep doing this. And eventually the idea is that you could come out with all finitely generated cohomology modules just from starting with these two subcategories. And we'll see how this works as we go along here. Okay, so let's look at no cohomology modules for a moment. Well, first of all, we should get a couple things straight. I really only want to talk about modules in the principal block. That is to say, we have blocks. That is, if you take KG, the group algebra, it always decomposes. So it always decomposes as a direct sum of two-sided ideals. Okay. I mean, this is just, this is a finite dimensional object. You just write out the biggest two-sided ideals of the smallest two-sided ideals that you could get like this. And you get a decomposition like this. And then the identity element is going to be, since this is a direct sum, is going to be a sum of elements in this. All right. And these things are going to be central idempotents. And then what happens is if you've got a module M, it's always going to look like, well, I can write it as 1 times M, which there will then be the sum of these EI times M. And these EI times M, because of the fact that these are central, these are submodules. Okay. And so what happens is that this is going to be decomposed as a direct sum of submodules. All right. Now, if M and N are in different blocks, and it will always be the case that hom kg M is 0. Okay. Will always be that case. And so in particular, what we usually do is the following. We write it this way. We choose something that we call we choose something that we call the principal block. And that's the block that you see, if M were an indecomposable module, then only one of these would be non-zero. Okay, because it's a direct sum. So the principal block is the block that contains K. Contains the trivial module K. Since we're interested in hom kg km, this is the same as X, if you like, kg km. That would be X0, but I mean, you know, but this is what we're talking about. If the point is if M is not in the principal block, then X star GM is going to be identically 0. Because I can't have any map from K into it, and I can't have any map from anything that we build from K in it. So those are in some sense no cohomology modules, but those are not what I'm interested in. Okay, what we're interested in are the ones that are actually in the principal block. Okay, so what we're interested in is let's call it M. It's maybe we'll say subcategory of ST mod V0. V0 is the principal block consisting of no cohomology modules. So that's what we're interested in. All right. Now, what I'm going to tell you now goes back probably, well, more than 30 years, actually. Because Dave Benson and I and Jeff Robinson were interested in this. What do these modules look like? In other words, here's the question. How do you make a no cohomology module.
Did you say this already, like projective or injective as a cohomology? Is that, or is it, that's not quite right?
I'm trying to get away from injectives and projectives. I want non-projective, non-injective. But I'm doing this in the stable category, so projective should be zero. No,
But if they were injective, they would have just cohomology. Or
that's correct. And in fact, we're over a Frobenius algebra. So injectives and projectives are the same.
You've already got that all we use anyway.
Yeah. So I've already covered this. You just didn't know it. Okay. All right.
I knew it, but I didn't know it.
Okay, so how do you make a new cohomology module? Let's see. Do the.
What's the significance? Is it sort of like an inject? I mean, what is the significance of a no cohomology module?
Well,
if there's any intuition then.
What we knew was that it happened occasionally. I mean, what we want to know is what does cohomology measure? Okay, let's put it that way. And what we had actually figured out was that it actually missed some stuff. So the question was, what was it missing? And then you know, and it's the same question. Well, I've just erased it, but when it comes down to Green-Lee's conjecture, the question is, if you take the submodule generated by the cochains on the solo subgroup, what are you missing out of that? Can you get everything? And well, we'll talk about that in a minute. Yeah, we don't know the answer at this point. But okay, but that's the question. What is it that we're missing when we just use this cohomology as a measure of the module? So how do we generate a new cohomology module? Well, here's the idea. I'll write it down for you very quickly. Here's the idea. Suppose we've got a subgroup H. H and KH has a non-principal block. Then what do you want to do? What we want to do is we want to take a module, and say in this block. So H is contained in G. I want to induce N up. In other words, I want to do the usual change of rings here, where I take KG, I'll tensor it over KH with M. Okay, this we write as N induced to G. This is a usual notation. So we'll do this. We'll do this induction, and let's suppose this has a summand. And B0 in the block of G, principal block of G. I want to claim that that submodule would then be a no cohomology module. And the reason is because you've got something called the Ekman-Shapiro lemma. That is to say, if I start with H star, G with coefficients in this N, induced to G, that's isomorphic to H star. H with coefficient N, but we've already said that N is not in a non-principal block. So that's the Okay. And so it will, this will also be true for any direct summand. This distributes over direct summands. So it would also be true for any direct summand event. All right. So this is a way of getting no cohomology modules. Is you take this thing, you induce it up, and if you've got a module that's in the principal block, then you get a no cohomology module. And basically, this construction is it. I mean, this is how you do it. All right. And in fact, well, let's see, what do I want to say here? Oh, yeah. Okay. And in fact, you know, what the theorem that we proved. So this is a theorem of that I proved with Dave Benson and Jeff Robinson back about 1990, something like that. Goes like this. That goes something like this, that there are no cohomology modules, non-trivial, let's say non-trivial. No cohomology modules. Zero. If it only every P element or P subgroup, let's put it that way. Is P element. So this sort of explains what was going on, and it's, as I say, it is basically this construction. You all know what P-nil potent means. So let's say P has a normal P complement. And I wrote this down wrong. I'm sorry. Let me correct myself here. Not every P subgroup, every centralizer of P subgroup. Of a non-trivial. Okay. It has a normal P complement, meaning a subgroup N contained in G. That's order of N is not divisible by P, and G mod N. And this is normal in G, and G mod N is a P group. So this is sort of a complement to the solo P subgroup. And this is what we mean by a normal P complement. And what's the point? Basically, it comes down to one particular idea, is that if the centralizer of P subgroups and P elements are all P nilpotent, then when you start to do this process, what you get is sort of all of the non-trivial subgroups that you would want to use here are have no non-principal horns. So you cannot construct anything this way. And that's basically what it comes down to. If these things are all centralizers are all P nilpotent, then we cannot find a subgroup H of it that will give us a that will give us any sort of module in this form, in this way. Okay. So in this particular case, let me just write it down. The corollary in this case. Which actually is, was noticed first by Dave Benson, is that Greenlee's conjecture holds if you have this condition. Okay. Because basically in that case, a finitely generated cohomology module is going to have to be actually equivalent in the stable category to a finitely generated module. All right. So that's what happens there. So this is great. All right, this is good. All right, we know some things what Greenlee's conjecture holds. All right. Now, let me do an example. Okay, and you'll see how some of this stuff works. So we're going to be very specific here, okay? I want to let G be C3 plus S3. So this is a Dirichlet group of order 3, say generated by X, and S3 is a symmetric group on 3 layers, so it will be generated by Y and T. And so your relations are going to be X cubed is 1, Y cubed is 1, X divides with Y and T, X, T equals X. Well, what about T? Oh, well, T squared is 1. T is a 2 cycle in this symmetric group. And so what does T do? Well, T, Y is going to be Y squared T. In other words, conjugation by T inverts Y. All right. This is symmetric group on 3 letters. That's all it is. I want P to be 3 here, in case you haven't guessed. Okay. And we'll look at some subgroups of this. Let me set some notation. I want to let X be little x minus 1. And I want capital Y to be Y minus Y squared. All right. So these have a particularly nice property. That is X cubed is equal to 1. It's also true that X cubed is equal to 0, which is also equal to Y cubed. T commutes with X. But what does T do to Y? Well, T interchanges Y and Y squared. So it's going to give you minus T, right? So you're going to get that thing. Now, let me look at, I want to set a subgroup, which I'll call H. So let me let H. I'll point out something, by the way, in advance here. You will notice that the centralizer of Y just consists of X and Y. So it's a P group, so it's P nilpotent. The centralizer of X, on the other hand, is the entire group, and that is not P nilpotent. Okay, so we're going to get something out of this. So what I want to do is I want to let H be the subgroup generated by X and T. Okay. And I want to define two irreducible modules. Well, one is K, this is the trivial module. And the other is I'll call it epsilon or E. And that's a KT module on which T acts by multiplication by -1. Because we have a normal P subgroup, that means that the solo subgroup is going to act trivially on every simple module, every irreducible module. And so on T, say this is K times an element M, and what's going to happen is xm equals M equals Ym. But what happens to T? Well, Tm is minus M. Okay, just acts by multiplication by -1. Okay, so these are two trivial modules. And in order to confuse you as much as possible, I'm going to consider them sometimes modules over KH, sometimes as modules over KG. They sort of make sense in all of those cases. All right. But here's KH, all right. Right. Let's look at the blocks of KH. Here's the point. I can write two item books down. E0, which is 1 plus T divided by 2. I'm dividing by 2 because I'm in characteristic 3, I can do that. And E1, which is I think I want T minus 1 divided by 2. These are item books. E1 squared equals E1, E0 squared equals E0, E0, E1 plus E1, E0. So they are two item books. So I can always write KG as KG times 1, which is KG times P1, E0 plus KG and E1. Because after all, 1 is equal to E0 plus E1. Is that right? Maybe I won't run a state that. Yeah. Oh, okay, sorry. Let's make that 1 minus B. Okay, that'll be fine. All right. So 1 is E0 plus P1, and they're orthogonal atom books. I can also write KH as KH times E1, E0 plus KH times E1. Okay. Now there's the difference here. In the case of KH, this KH is an abelian group, and consequently, this E0 and E1, these are central idempotents, and I get a decomposition of blocks into two-sided ideals. Okay. For KG, they're not central. This T does not commute with Y. And so something else is happening here. You have to be more careful. But this is still a direct sum as vector spaces or as left ideals, but it's not a direct sum as two-sided ideals. These are not two-sided ideals. So this has a non-principal block. This one does not. Okay. So let's take an element in the non-principal block here and run this up. Is it still up here? Yeah, so run this thing on it. Okay. What's the element in the non-principal block? Well, it says E. So I'm going to look at it as a module over KH. I want to induce it to G. So that's going to be KG tensored with E over KH. Then I want to see what kind of module that is. What does it look like? Okay. Well, let's see. I guess I can. So as I say, we're gonna follow this scheme. Well, anything in KH just acts naturally on the T times, is necessary, so I'm not going to worry about X. Capital X is going to kill everything. What I'm worried about is Y, because there's E induced to G as a basis, which consists of basically one tensor E. Let's write E as K times M. That's one tensor M, Y tensor M, and Y squared tensor M. Okay. Now, what I'm looking at is what happens with T. So this, I'm sorry, I should put it in tensor. What happens with T? Well, T times one tensor M is going to be, well, it's one tensor Tm, which is minus one tensor. Okay. And T times Y tensor M, little m, is going to be, well, if I pull the T past the Y, I get a minus sign. I'm sorry, I need to pull the T past the Y. I didn't do that right. T tensor M. The T now crosses this thing and I get another minus M. So what do I get? I get Y tensor M. So T times Y tensor M is Y tensor M. And T times Y squared tensor M. Well, it's the same thing. You have to pull the T past two Y's, which means you get a minus one or another minus one, which gives you Y squared tensor M. Or minus sign. Okay, so what does this mean? I'm gonna write the module this way. I'll write it back. I will write it as E. And then multiply by Y, you get K. And you multiply by Y, and you get E again. In other words, it has three composition factors you get from one to the other by multiplication by this Y. Okay, X acts trivially on this. Okay, so in order to, I'm usually going to write it as E, E, just like that. Right, that means going down is multiplying by Y. So this is what it looks like, and that is a no cohomology module. It's in the principal block, but it was induced from something that wasn't in the principal block, in another block. So it is a no cohomology module, and actually you can see this if you like, if you write down the projective cover. The projective cover of this looks like this. It's E, K, E. So this is by Y going down this way. If you go by X the other way, and you get another copy of it. And so this is multiplication by X, this is multiplication by Y. And that's what it looks like. It's a 9-dimensional module. These things sort of represent, each node here represents a basis element. So that's one, that's capital Y, that's capital Y squared. This is X times capital X times capital Y, etc. So that's what it looks like. It's a 9-dimensional module. If you want to take the map the projective cover onto here, what's the kernel? The kernel is this thing. Okay. And now you map the projective cover onto this, and what's the kernel is that thing. So you get the module back after 2 steps. So it's periodic, 2-step periodic. And it's a no cohomology module, as you can see. All right. So what do we do with this? Well, as I say, this is basically the story. This is basically what it's all about. All right. So having said all this, I will try to give you, I've got what, 5 minutes, maybe a little bit more. Let me tell you where, let's go back to where we started with this conjecture, or the equivalent conjecture of Benson and Greenleaf. And it goes like this. As I say, the story for me goes this way. I went to Bonn for the Alstorf Institute for this fall semester last year for 2 months. Dave Benson and John Greenleaf were both there. We got talking about this. Dave told me Greenleaf's conjecture of the equivalent one. I thought it was totally preposterous. Just couldn't believe it. Dave thought it was true. We spent a large part of the semester pushing pieces of paper back and forth, where I would try to get a counterexample. I would try to prove it. Finally, at the end, it was actually after I left, in around the 1st of December. I looked at all that we had done, and all the little calculations we had made, and suddenly realized that in particular cases, it was actually true. And the cases were, we have 2 cases. A is C. Actually, you can do 3 to the n for any n greater than or equal to 1 across F3. The other case is case A, case B. That G is C2, cyclic group of order 2, cross with an alternating group of order 4. Okay, and in both of these cases, here's the theorem. Here's the theorem. In both of these cases, the Greenleaf conjecture holds. Okay. And let me take 2 minutes, and I will give you a very, very fast sketch of the group. As what you do is you suppose you have such a module. Finitely generated cohomology model. Okay, so the first thing you do is you note that kg of mk is finite dimensional. Okay, so what you do is you take the intersection of the kernels of all these maps. Okay, there are only a finite number of them. I mean, you just have to do a basis, and you get a map. M onto some of copies of K. And this has what you get N here is has the property that kg NK. Right. Well, that's the first step. So the other one is you do the same idea on the other end. Is you get N with kg and M equal I'm sorry, km equal. Now each time I have taken a submodule with a finite dimensional quotient. So that's fine. I'm still sort of in the same subcategory. I'm in the category, I haven't changed the category. If I can prove that N is in the category generated by these modules, then I prove that M is. And the same thing here. What I'm gonna do is I'm gonna factor out all images of maps of K into M. And so what we can do is we can assume that both of these are 0. And then what we have to do is we have to say, okay. And then what I prove as okay, here we are, we've got, this M, if I restrict it down to subgroup S3, the symmetric group of 3 letters, then this is a sum of copies of, well, E and this E, K, E. That's all you can get. That's what you have to have. All right. All right. And there are only a finite number here. Okay. So what you do with the rest of the proof is a war of attrition. Okay. What we're going to do is we're going to do induction on the number of copies of E. And it, you know, this takes several pages, but I mean, what you do is you just show, you pick one out. If it's in the circle, you just factor it out, and you've gotten rid of one of these. If it's in the top of the thing, you take the submodule, complementary submodule, and you've gotten rid of one. So it's whether or not it's in the middle if there's someplace. And when it's in the middle, then you've got to go through some process whereby you show that if you take out finite dimensional thing off the top and finite dimensional thing off the bottom, then you get rid of one. And then when you get down to this number being 0, then you want to prove that this is in fact a no cohomology module. And that's actually not so. But anyway, that's basically the idea. Have we given real evidence that Greenlee's conjecture is true? I'm not so sure. But it's going to be, there are going to be some cases where it's true. There'll probably be more. But that's how far we've gotten. So thank you.
So I was just trying to think what the topic, does any way to topologically understand this? Like, so I started thinking of like C star VG is sort of like BG.
Yeah.
C star VS is like VS, and then the BG module over C star VG is like a space mapping to BG.
In some sense, yeah.
And then, so is something saying like some spaces mapping to BG is related to something about a space mapping to BS, but I don't know what like being generated would mean in that. Like I don't know a topological translation of that.
It sort of says that everything's controlled at the level of the Solow subgroup. And you've got, I mean, you control things by the level of the Solow subgroup and these connections between the different copies of.
Yeah, I was just wondering if there's like something like could you interpret like the idea of something mapping to BG and this being generated as something mapping to ES or something like that? Yeah, like I don't know, I was just trying to think like is there some like topological way to understand this condition of being generated by this, thing?
I'm not sure that it follows exactly topologically.
Yeah.
I mean, you probably John Greenlee has a very good idea of why he's doing that. But I mean, the reason why I'm doing it is because this is sort of a tip of an iceberg. I mean, there are a whole bunch of problems that are like this, and trying to get some handle on what these infinitely generated modules are and how they relate to everything. And so there's something that we're leads on our work.
It is a complicated thing.
It is indeed. It is indeed.
It's working twice, and so you still think there's a counterexample, or?
Personally, I would, I don't know that I'd bet my house on it, but
Thank you.
but I don't. I think when you get into higher stuff, larger groups, you're going to have real problems with something funny there. But I don't know how to do it. We're still working on it.
We have a general idea, but like, what is it about these groups that are nice that let you exploit it, where you wouldn't be able to, or to do something like that, the nice composition theory?
Well, part of it is this. Is that we can get down to, you know, something that, where we really have a good handle on what the thing is. And you can't do that, but you can do this. Is, well, I mean, the technical term is that the nucleus of the variety is, has the one, but in general, this is not gonna work. You're gonna have many more types of no cohomology model, to be much more varied.
So I guess I want to ask about, sort of on that note about the no cohomology modules. So you kind of said that they all come from this construction
Yeah,
in some sense. But I guess the only precise statement you said was that if there are no subgroups for which you can do this construction, then there are no cohomology modules. But is there, in the case where there are some, can you formulate the precise sense in which they kind of generate the no cohomology modules?
and, well, what you can do is you can generate the category, let's put it that way, from these ones that you get by this method.
Just in generated in terms of like shifts and.
Yep,
cones
like
or
the
more
triangulated category. Where you
Okay,
put
generated
together
as a
as
triangulated.
a triangulated category. Yeah.
Questions? That was John F.